The last thing that we're going to be working with today is determining where your graphs have vertical tangents. Remember that vertical tangents, or vertical lines, have slopes that are undefined or there is no slope. Remember, now we're dealing with implicit curves, so the curves don't necessarily have to be functions. They can be relations that look like this. So note, at one end, you can have a vertical tangent to your graph. Remember, vertical tangents come in the form of x equals to some number since it's a vertical line. If we want a vertical tangent, which means that our derivative has to be undefined, it's going to be very similar to finding when we have a horizontal tangent. First, we're going to see where is our derivative undefined, solve for those values for those variables, and then we just need to check if those coordinates actually lie on the graph. So let's start with y squared equals to x squared minus 4 over x squared plus 4. First, let's find our derivative. We have to use implicit differentiation starting with 2y. Don't forget your chain rule on the y, so dy dx is equal to, on the right-hand side though, we're going to have a quotient rule. So we have the low times derivative of the high minus high derivative of the low, all over low squared. So we have x squared plus 4 squared. Note that this expression here, right, we did not use a chain rule on the right-hand side. We did, however, remember, x is already an expression in terms of x, so we didn't have to write dx dx. Now, let's clean up that top on the right-hand side. So dy dx, and I'm going to keep the 2y over there for now. We will distribute our 2x. That will give us 2x to the third plus 8x minus, let's distribute that 2x. I'm also going to distribute the negative while we're there too. That would be minus 2x to the third, and that would be plus 8x all over x squared plus 4 squared. Again, we can combine our terms in the numerator. The 2x to the third and the negative 2x to the third will cancel. We'll be left with 16x on top, and we have x squared plus 4 squared. Note that we still have 2y dy dx is equal to that derivative there. We haven't finished solving for dy dx. We can multiply both sides by 1 over 2y to get rid of the 2y's. And now you're left with dy dx is equal to 8x, just reducing the 16 and the 2, over y times x squared plus 4 squared. Just going to move these up so we have a little bit extra room here, okay? But we already have our first derivative. Now that we have our first derivative, we can say, all right, when is this derivative undefined? Remember, derivatives are undefined, or fractions are undefined, when your denominator is equal to 0. If we set y times x squared plus 4 squared equals to 0, notice we have two factors that are equal to 0. That would mean either y would have to equal to 0, or that would mean that x squared plus 4 squared would have to equal to 0. If we look at the first case, we already have y equals to 0. In the second case, however, x squared plus 4 squared will never equal to 0. That's got to be a positive number. Therefore, there's no solution. So we know that our y coordinate here is going to be y is equal to 0. However, remember that vertical tangents come in the form of x equals to some number. So we got to make sure that there even exists a point on our graph where y is equal to 0. Well, we know that the original equation was y squared equals to x squared minus 4 over x squared plus 4. If we use the value that y is equal to 0 and we substitute that in, we have that 0 squared, or just 0, will equal to x squared minus 4 over x squared plus 4. If we go to solve for x here, we can either cross multiply or multiply both sides by x squared plus 4. We're going to wind up with x squared minus 4 is equal to 0. If we factor here, we have x plus 2 equals to 0, and we're also going to have x minus 2 equals to 0. I can factor that first. X plus 2, x minus 2 equals to 0, and then we have x plus 2 equals 0, x minus 2 equals to 0, and x will equal to a negative 2, and x is equal to a positive 2. That means that there are two coordinates on our graph. There are two coordinates on our graph where we have vertical tangents. The coordinates are going to be at negative 2, 0, and at positive 2, 0. However, if they want the equation of your vertical tangent, the equation of your vertical tangent is going to be x equals to negative 2 and x equals to a positive 2. You can actually go to Desmos and graph the original equation here to justify that these are the coordinates and these are the equations of your vertical tangents. If we utilize Desmos and we plug in the original function here, which I actually already have graphed for you, note when you're looking at the graph here, when x is equal to 2, or negative 2 I should say, and x equals to positive 2, not only do you have here two different roots for the function, but we also can see that these are coordinates where we have vertical tangents. If I were to plug in the equation x equals to negative 2, you can see that both of those graphs have the same coordinate, and we can do the same at x equals to 2, where the graph also has the same coordinate there. So note, again, going back, we can actually say that if our graph is going to have a vertical tangent, we're going to take our first derivative and figure out where it's undefined. That's when our denominator is equal to 0. We're going to take those coordinates and make sure that they exist on the graph. And then we're going to just go back to the question and make sure that we're answering it. In this case, they're asking for the point at which we have a vertical tangent, which we answered. And they also want the equation of the tangent lines, which in this case is x equals negative 2 and x equals 2. Please make sure to complete the rest of this file for classwork and make sure that you submit.